All right. Hello, class. Um, I am pre-recording this lesson because I'm going to be absent um, on the 16th. So you guys are going to watch this lesson. You are going to fill out the attendance form. Um, Pause the video, fill out the attendance form right now. Okay. Um, on Canvas, I added a check your attendance button. And on that check your attendance button, you can see whether your attendance went through or not. And if your attendance did not go through and you can't get it to go through, you need to send me a Canvas message. Okay? If you send me that Canvas message and it's not during your class period, I'm still not going to mark you as present. Okay? You're supposed to watch this video during the time for your class, whether it's period 4 or period 6. Okay? So with that being said, I have a pretty quick lesson for you today. All right. So today, what we're going to talk about is energy dissipation and the mass spring system. Okay. So in reality, friction acts on the mass as it oscillates back and forth. Okay. So when I introduced the mass spring system to you, I specifically said it's a frictionless surface. There's no air resistance, but none of that is going to be. It could be approximately true, but it's not going to be exactly true in a real mass spring system. Okay. So we could come up with a model for the drag force. Okay. So so we have a model for the drag force. All right. This is the model that is typically used when you're talking about energy dissipation in the mass spring system. So that model for the drag force is minus a constant times the velocity. Okay. So this minus sign indicates that drag is an oppositional force. All right. So in other words, if the velocity is positive, then the drag force is going to be negative. Okay. So if you're moving to the right, if you're sliding to the right in a mass spring system, drag is going to push you to the left and try to slow you down. Okay. And then furthermore, if you're sliding to the left, then your velocity is negative, so you have a double negative, and the drag force is going to be in the positive direction, which is to the right. So no matter which way you go, the drag force is going to be trying to slow you down. Okay. C is a constant called the drag coefficient. And so basically that the bigger the C coefficient is, the more drag you have. Okay, so the rougher the surface is or the thicker the air resistance is, something like that. And then V is, of course, your velocity. So this has a sign on it. It can be positive or negative because it's a velocity, not a speed. So when we have this, we can revisit the equation of motion. All right. So if you recall, how did we get the equation of motion for a mass spring system? Well, we had Newton's second law, okay, net force equals ma, all right, and all right, net force equals ma, and the net force now is not just the elastic force, it is the elastic force and the drag force. So we have minus kx and we have minus cv equals ma. So we have the elastic restoring force and we have the drag force. All right. So what is the effect? Okay, so the question is, what is the effect of drag? And it's really quite simple. Let's suppose that your position time before drag is going to look like this. All right. Once you include drag, your position time is going to look like this. So basically, the amplitude is going to get smaller as time goes on. So it's going to go like that. Okay, so this is no drag, and this is with drag. So this is the main thing you should know, is that it turns the position time graph and it makes the amplitude drag makes the amplitude decrease with time. Now, quite predictably, more drag means that the amplitude decreases more quickly. Okay, so if we had more drag, this amplitude might shrink to zero almost immediately. Okay, so yeah, in any real simple harmonic motion system, there's always going to be some drag, and so in that case, it is going to cause the amplitude to go down slowly or quickly, depending on the amount. You could also draw a graph of the energy. So I'm going to draw the mechanical energy. So if you recall, mechanical energy is all forms of energy. So anything but heat. Okay, so mechanical energy does not include heat. And so if you have no drag, the mechanical energy as time goes on is just a constant, right? So your graph of mechanical energy versus time is just going to look completely flat. Okay. But if you have drag, the mechanical energy versus time is going to look like an exponential decay. So it's going to slowly go to zero. Not in a linear fashion. So this is not a straight line that goes to zero. It's curved. Okay, it's curved. Exponential decay. So it gets closer and closer to zero as time goes on. So this should just slowly decrease to zero. Okay. So this is with drag. And so, of course, this mechanical energy is going to become heat. So just to remind you, mechanical energy in this case would be kinetic energy and potential energy. All right. Can we work out the mathematics? Could we actually get the position as a function of time? Yes, but the math involved is college level math. So if you take in engineering physics, like specifically mechanical engineering, electrical engineering, you'll learn a lot about this stuff. But it's a little bit beyond the scope of this course to actually work out the math. So you just need to know qualitatively the effect of friction. It's just going to make the amplitude go down. There's one more thing I wanted to talk about, which is something called the driving force. Okay. And so basically a driving force is a force that makes simple harmonic motion begin. Okay. You need a force. If you have a system, you need a force to make it start moving. You need to give it that initial kick in order to make it oscillate back and forth. Okay. So that's called the driving force. All right. So oftentimes, all right. So what will happen is if we go back to the equation of motion, we have net force equals ma. All right. The net force in this case is going to be the elastic force, the drag force, but then we're also going to include the driving force. Okay, and the driving force is some function of time. So again, we have elastic, we have drag force, and then we have driving force. Oftentimes, the driving force is periodic. So what that means is that the driving force is represented by a sine or a cosine. So it's like you're just pushing regularly. Okay, you're pushing the mass, then you're waiting a little bit. And you're pushing the mass, and you're waiting a little bit. You're pushing the mass, and you're waiting a little bit. So what you want to think about is if you're on a swing, okay, if you're on a swing, you're kicking. Your kick is the driving force to keep swinging, and you're kicking periodically, right? Every time you swing, you do a kick. All right? So that's what that driving force is. That's what a periodic driving force is. Now, so the question is, well, what happens if the period of the driving force matches the natural period. Okay? So in other words, the natural period for a mass spring system is just going to be 2 pi square root of m over k. So what happens if you are pushing the mass spring system once every second? And what if the period is 1 second? So then basically you're pushing it at exactly the same point in the motion every single time. Okay? Or if you're on a swing, you're kicking at the same point in the swing every single time. All right? Because you don't have to do that. You could get into a swing and you could just kick frantically, okay, if you wanted to. Nothing's going to happen, but you could just kick frantically in a swing. Or if I'm in a mass spring system and I'm trying to disturb it, I could just push. I could just go blah, 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 and where I have no rhyme or reason to how often I'm pushing it. That's not going to do anything, okay? But what happens is if you push in sync with the motion of the object, so in other words, if you're on a swing and you kick every time you're going down, and you kick every time, or if you push at the same point in the motion every single time, what you're going to get is a position time graph that looks like the opposite of what we saw with drag. So what's going to happen is you'll start off with no motion, and the motion will grow, and it'll get bigger and bigger and bigger as time goes on. Okay? And in fact, it'll keep growing until the drag force becomes so large that it can't grow anymore. And so when that happens, so if your driving force happens to match the natural period of vibration, so you're kicking in sync or you're pushing in sync with the natural vibration of the object, the amplitude will grow. As time goes on. All right. And so if you have a driving force that makes the amplitude grow as time goes on, that is called resonance. So resonance is when the amplitude grows as time goes on because there is a driving force that is going in sync with the natural vibrations of the object. Okay? And so resonance is can actually be a really bad thing sometimes, and sometimes it can be a really good thing. I'll give you an example of when resonance is a bad thing, okay? What if you have a building? A building will have a natural frequency. So in other words, if you took the building, let's say this is the building, and you tip it to one side, it is going to rock back and forth slowly. It'll go, and eventually it'll come back to straight up and down. Now, what if you had an earthquake, and the earthquake is rocking the building back and forth at its natural frequency? So what that's going to do is it is going to make the building rock back and forth, and the amplitude will grow as time goes on until the building tips over. Okay? So in building design, you want to make sure that the natural frequency of your building, because any structure is going to have some natural frequency where it just, you disturb it and it just vibrates at that frequency. You want to make sure that that is not the same frequency as earthquakes. Otherwise, if an earthquake happens, you're going to resonate with the earthquake, and the building is going to have really large vibrations, and it's going to fall down. Okay? So in engineering, you oftentimes, in structural engineering, you want to avoid resonance at all costs by thinking about what kind of driving forces is the structure going to have in its natural environment. And you want to make sure that the natural frequency of your structure is nowhere close to the frequencies that it's going to encounter in the environment. Okay? So can you talk about the physics of resonance in terms of equations? Yes, but that also is beyond the scope of this course. And so really I just want you guys to know about this stuff intuitively. So there is no mathematical assignment. There's no quiz for today. It's just you need to know qualitatively what is a driving force and what is a drag force and what effect do they have on the position time graphs. Okay, one effect, so drag force makes the amplitude get smaller as time goes on. Driving force makes the amplitude get bigger as time goes on. And those two things are competing against each other. Okay? I'm going to remind you one more time to fill out the attendance if you haven't already. And have